Okay, welcome everyone. Today we're talking about hidden Markov models. It's a core concept, core topic in artificial intelligence. We'll try to do this in under 10 minutes. Let's go. So a hidden Markov model, as the name suggests, is a model where the true state is hidden. It can evolve, and it also manifests a certain outputs. We observe those outputs. We also call them to be the effects or evidence or emissions at each step. So there's a hidden layer, we call it the X layer, and the observation layer of the E values. And we want to infer the hidden layer from those observations. A good example can be that of medical diagnosis, where the patient's actual condition is not visible, but the doctor can observe symptoms such as fever, oxygen saturation level, PCR results, etc. But the actual condition such as tumor, benign tumor, etc., is not directly known. And we have a certain likelihood of those health states transitioning, as well as displaying those particular observations, the correlation with those symptoms. And using that, the doctor has to do the best estimate for the hidden layer so as to recommend the best treatment option. So HMMs are a core purpose technique, and they are a general purpose technique. So they have many different applications. You could apply them to speech recognition, medical monitoring, machine translation, robot tracking, etc. Okay. We start our understanding of the HMM problem by using this toy problem of given two kinds of coins, a fair coin and a biased coin. And the fair coin is a coin that lands on heads and tails 50% of time. And a biased coin gives just heads all the time. Okay. Now your toy problem could be different. You could have 2 coins, 3 coins, slightly different distribution, etc. And let's suppose we're given the transition probability as well, that given one coin, the same coin will be used in the next step 90% time, and 10% time, the coin will be switched to the other coin. Again, this thing could change as well. This is just a toy problem for us to understand HMM. Okay. Now, in this case, let's suppose we're given an observation sequence of 100 coin tosses, heads, tails, etc. And what is the underlying hidden model that best explains this observation sequence? That's referred to as the most likely explanation problem. So in other words, we're trying to determine when was the fair coin used, when was the biased coin used, and that really is the HMM problem, HMM MLE problem. Formally, we would say that we're given the states, we're given the observations, we're given the initial distribution, we're given the transition probability, and we're given the emission probability. Now we want to identify the states X, the hidden layer, that best identifies the emissions 1 through n that are given to us. And it's a famous Viterbi algorithm, so you can find many references for it as well. Okay. So let's walk through the algorithm itself. It's a simple dynamic programming algorithm. It uses an array to store the probability values. We'll take a look at that in a moment. And it simply builds it from left to right, observations going from 1 through n, and then it traces backwards to generate the sequence from right to left. So this is the algorithm in its entirety. We can break it down into 3 phases. In the first step, we look at just the initialization. That's the first column, the first emission. We would say that we are looking at E1. And for each state j in 1 through k, we will say the MP, which is the dynamic programming variable, maximum probability. MPJ1 is equal to initial probability for that initial j times the emission probability for the j through E1. It might help if I show you this matrix first. This is the matrix that we're really building out in the initialization phase. We're really just building the first column, but this is the two-dimensional MP matrix that we're building out. So if we go back to the algorithm, in the first initialization step, we are just building the first column. So MPJ1 is equal to initial j times MJE1. Then we start building each column by column. So that's the dynamic programming recursive step going from left to right. For each observation I in 2 through n, 2 because we already built out 1. And for each state j, those are the rows of the matrix, MPJI is equal to maximum value of looking at the previous column, looking at the state that gives us this best product. The product in this case is the MPZ I minus 1, that means the previous column, look at all possible states, the maximum probability for that state, times the transitioning from that state to the current state, times the emission probability for the current state to give this EI. Now you might observe that in this max Z, the last term does not have anything to do with Z, so you could theoretically take it out and multiply it after. That's perfectly fine as well. And once you identify the max Z, then you store the previous J as well, so you can later on backtrack. And that's basically what we do in the reconstruction step. We go from right to left. First of all, we look at the last column, see which value is highest, and then we simply follow the back pointers to go across each of the columns and identify which state corresponded to that. And so finally, we have the value of each X, which has as many values as the number of columns that you have, and then you return that. That's the Viterbi algorithm. Let's look at the key recursive line together. MPJI is equal to maximum of MPZI minus 1. So let's look through this matrix. We're trying to build out this cell in the dark color. And all we look at is the previous column, all of the values, MPZI minus 1. So this Z in this case is 1, Z is equal to 2, Z is equal to K, etc. And then you will multiply that particular value times the transition from Z to K. So the Z to J, which is the current one we're building out, times the emission from the current Z to give that EI. Like I mentioned, this part is not in your max Z, so you could theoretically put the max, break it over here, multiply it later, perfectly fine. So that's the three things that the key recursive line does. If we want to apply this to our toy problem, we would say that in this case, there are only two states, fair coin, biased coin. And let's suppose you're building up the 15th step here. Then you would look at the 14th column. So MPB15 is equal to maximum over MPZ14 times transition to the current state times the emission. So essentially looking at maximum over these two values, B14 times transitioning from bias to bias times the emission of B15, or F14, the previous, this cell transitioning from fair to biased, and then displaying BE15. So that's basically the Viterbi algorithm time complexity, as you can easily observe that in this, because it's a dynamic programming algorithm, you have n columns, k rows. So your data structure that you're building out is of size nk to write each cell. It takes you order of k time. So the total time is order nk square. Now, if your k is small, like 2 or 3 or something, so it's a logical constant of the problem, then it's pretty much a linear time algorithm. If k is not a logical constant, such as you're looking at, the robot could be in 10,000 different states, 10,000 different areas of the field that you're looking at, then it's not a logical constant, rather it's an enumerated constant, enumerated value. In that case, this approach might not be most efficient because you're doing nk square. So if your n is 1,000,000 and k is, let's say, 100,000, then this algorithm starts to become not that efficient, and then there are other techniques to consider here. If you want to play with the source code, feel free to download it from the GitHub repo that I link below. If you want to make changes to it, just send me a pull request. But otherwise, just feel free to clone it, run it, and have fun with it. There are only 3 relevant files: HMM evaluator, which is just your main function, and the Viterbi, which is the algorithm that we discussed here. And to summarize, HMMs are very important models, machine learning, AI models, in which we try to guess the hidden underlying state by observing the emissions using the probability calculations. Viterbi is the DP algorithm that we discussed. There are a few additional topics. You may have to prevent the underflow because when you're trying to multiply many different probabilities, you can end up with a 0. So the source code explains that a little bit, but look out for a separate video on that topic. Similarly, you may have a slightly different problem that you want to see what's the probability of the sequence, observation sequence itself, that you can use using a forward algorithm. similar but slightly different. You have to take the sum instead of the maximum. And also, like I mentioned, if your K is too large, your state space is too large, then instead of this, you could do a slightly different approach called the particle filtering. Again, look out for separate video on that. But that's HMMs, that's Viterbi. Have fun learning. Okay.